Hello. Today we're going to be taking a look at transformations, specifically transformations of functions, not like transformers or anything. The nice part about this is that I'm going to be using Desmos to demonstrate most of it so you can see it kind of dynamically. Also, it means I don't have to write as much because you can take notes. So let's hop over to the actual note that I won't be writing down. And I want to show you that we're going to be taking a look at what happens when we deal with functions that look like this. Now, if you're anything like I was when I was a student, or frankly like I am now, that is terrifying. There's a lot of stuff going on there, almost too much for the brain to comprehend. So I'm going to try and walk you through it just a little bit and hopefully take away some of your apprehension. Start with basically the base function. I'm just going to write over here on the side because, that's not the tool I want. I'm going to write over here on the side just so that you can see what I'm talking about to build that up. In order to explain that formula, I'm going to start off with y equals f of x. And then what I want to do is build up to this, but I want to do it kind of one variable at a time so you see what happens. If I want to introduce the variable a, it goes in front of f of x. If I want to introduce the variable c, it goes at the end after f of x. If I want to introduce the k, it goes in front of the x in the f of x. And if I want to introduce the d, it goes with the x to the right of it. And just to be technical, use square bracket there, it should be kx minus d plus c. And the order on that matters, and we'll see later how that actually plays out. But those four variables, a, k, d, and c, all have an effect on the transformation of the graph. Probably you know what most of those are just from previous year's work. All right, so I've put in the base function here. In this case, it's a cubic. That's actually what's on your sheet. I don't know if you really even noticed that it was slightly different, but yes, it is a cubic. So let's see what happens when we introduce each of the variables here. So I'm just going to put an a in front. And now, most of these are things that you've already done with linear functions and quadratics in grades 9 and 10, and you've done it with plenty of them in grade 11. But just as a reminder, what happens as a gets larger is we stretch upwards. If a gets smaller, i.e. smaller than 1, we compress vertically. So up and down, it gets fatter and fatter and fatter. If we hit 0, we go to flatness, which makes sense. That's just y equals 0x cubed. And as we go negative, it just flips it upside down. So we get a vertical flip. So vertical stretch, vertical compression, and negative flips. By the way, you're welcome to set this up in Desmos. Just type in what I typed in and play with it yourself. You can set it up with more than one variable. It just sometimes you have to put a couple of numbers in, set a few things constant, or Desmos does not like it. Okay, so that's the A. The K goes in front, and it actually goes exactly where the A did in this particular case. For now, I know you're going to want to think A and K do the same thing. They don't. I can prove it with different functions. And you know what? I might take a break just after this and try to explain or show you a function where A and K do different things. For polynomial functions, A and K look like they're doing the same thing. But I want you to think about it a little bit differently. So when I increase this, I know, again, this is doing exactly the same thing that you saw with A, but now I want you to frame it differently in your mind. Instead of thinking this as a vertical stretch, I want you to visualize it as a horizontal compression and see that it is getting thinner. Thinner side to side anyway. And as I go towards the negative numbers, it flips it vertically. Flips it horizontally in this case. Again, technically it doesn't either way, but for our purposes, I want you to think about K as being entirely horizontal. Okay, I will come back to that later and we will explain how those are different things. Alrighty. Okay, so D, what does D do? Let's get rid of the K, put in the D. Now this one, I always have a hard time explaining this to students in a way that it makes sense. I'm going to start at 0. And you'll see that as D gets larger, it moves to the right. And as D is negative, it moves to the left. Now you have to be careful because it is x minus D. So for instance, x minus 3 is actually going to be going in which direction? X minus 3 goes to the right, 3. X plus 3 would go to the left. And it comes into the fact that we have the negative sign there, which seems like it's fixing it, but technically it's the opposite of whatever sign D is the direction it moves. So x minus 2 goes 2 to the right, x plus 2 goes 2 to the left, and so on. But that's what D does, moves it left and right. Now let's remove that. And I'll put a C at the end. And again, I'm going to start this one at 0. And you can see that as C gets larger, as we add numbers at the end, it goes up. And as we subtract numbers at the end, it goes down. Up, down. All right, and then you can start putting more than one together. Again, it doesn't particularly like certain versions. So I'm gonna just do the A here on this one. And then I can start doing things like I want to shift it over, and I want to shift it down, and I want to stretch it. And if I'd introduced a K, it would do the exact same thing A is, or at least visually would. A is all about vertical, and K is all about horizontal. Okay, so I said I would actually verify to you that A and K do different things. So I'm going to give you an example of a function that we're not into yet, but a trigonometry function. And I'm just going to do y equals sine of x. Now the way the notation works, and this is very subtle. Actually, let me change the scale there just a little bit so it's a little bit easier to see. Actually, let me change that to a 3 and a 3. That's better. Okay, so what I'm going to do is set both of these equal to 1 for a moment, and I'm going to put A in front of f at x. And now if you look really carefully, K doesn't go in front of f at x, it goes in front of the x in f at x. And again, with a polynomial function that's just x to a power, these aren't different things. But to this function, they definitely are. So with A, it should stretch upwards when I get bigger, and down when I'm, or get flatter when I go into the decimal numbers, and it should flip when I go negative. Okay, so hopefully you'll agree that what's happening here is definitely something vertical. Horizontally, it's not doing anything. You'll notice all the zeros, the x-intercepts don't change. It just stretches up and down. Okay, I'm going to set that back to 1. And now let's see what happens with the k. Now with polynomials, it looked like it did the same thing, but here you'll see a distinct difference. Here, as k gets bigger, it's not stretching upwards, it's compressing side to side. And as we go less than 1 decimal numbers, it's going to stretch side to side until we get to 0, and then negative numbers will flip it. Positive numbers, you'll see that it goes up to the right of the origin, and negative numbers, you'll see it goes down to the right of the origin. So A is all about vertical, K is all about horizontal. All right, I'm going to stop playing around there. Again, you can make these in Desmos and play around all you want. That's cool. But for now, I'm going to switch back to the transformations page. Okay, so again, you can fill in those boxes later. You don't need me to do that. I just talked you through it. Let's take a look at this particular function here. So we have f of x equals -3 times, and then in brackets, 4x plus 5 all squared minus 6. So let's start off with what is the base function? And that means what is the thing that we're going to kind of start by graphing? So there's a lot of transformations in there, and those transformations are caused by the numbers 3, 4, 5, and 6. But the base function is actually just a simple y equals x squared. The transformations that have been applied to that base function, well, the a value is -3. And what did it do? It's going to stretch vertically and cause a vertical flip. And I usually just abbreviate that with v flip. I often write v stretch as well. Probably should have here just to save time. But anyway, the k, again, always to do with the horizontal. In this case is 4. And its effect on the graph would be to compress horizontally by 4. I'm going to put a factor of 4. I'm going to actually go back to the a, and I said stretch vertically. I should have put by a factor of 3, just to be more specific, but that's okay. Okay, the d in this case, this is the one that people tend to mess up. Or I just mess up the marker. Here we have x plus 5. Because it's in the form of x minus d, d is actually -5. But again, x plus 5 will move to the left. So I'll just put down left 5. And finally, the c is -6. And what that does is down 6. And if we want, we can just take a moment and go back over to Desmos and see if that actually works out to be true. Okay, so let's get rid of this old stuff we had here. And I'm just going to do it one step at a time. So y equals x squared. I'm putting the bracket around it, not that it does anything now, it just makes editing it later a little bit easier. And we said that in front of that, actually let me replace that with square bracket. I'm going to put all the brackets in now. It'll make life easier later. Okay, so there's our base function, y equals x squared, with a few extra brackets that will eventually come into play. And then we said if we add the -3 in front, it should stretch it vertically. It should make it higher. So I'm going to put a -3 in front, or sorry, a 3 in front to make it higher. Why doesn't it like that? Apparently it doesn't want that many brackets. All right, we'll get rid of some of the brackets for now. Okay, there we go. We stretched upwards, and the negative sign should flip it. All right. I'm going to just turn the original one off for a moment so that we can focus on this one. And then the next thing that we said we did is take a k value of 4, which should compress it horizontally, making it even thinner side to side. Now, I have a feeling it's not going to like this. Let's find out. So -3. I'm not sure if it's the bracket it doesn't like. we got to put in 4x there. And yeah, that definitely did make it thinner. Maybe it just doesn't like the square brackets. Either way. Okay, so that made it thinner. I'm not going to turn that off for a second, just so we can see the newest transformation of the graph. Going to cut and paste it. Then we said we applied a d of minus 5. Now this is where we have to put a bracket around the x, because the d goes with the x, not with the 4x. So a d value of negative 5, since it's minus d, actually becomes plus 5. And that did shift it 5 to the left, as predicted. And then our final transformation, we said we would add a c value on the end, which in this case is negative 6, and it should move it down 6. And there we go. It just didn't quite fit on the graph. So that is the fully transformed version of the graph. So just to go back again, we started with that. We stretched it upward. We stretched it upwards and then flipped it. We then compressed it horizontally. We then shifted it 5 to the left. We then shifted it down 6. And there's our final graph. Cool. All right, moving back to our lesson page. This is the skill that I think is really valuable. A lot of teachers seem to like the whole idea of being able to graph functions. I find that a rather useless skill. As you've seen, we can punch anything into Desmos and get a graph out immediately, quickly, and beautifully. Learning how to do that manually seems like a big time suck and not a useful skill. Now, something that computers are not particularly good at is taking a graph like this one in A and finding out what its equation is. That, to me, is a useful skill, and still tests all the same things. You still have to know what each of the transformations does. So let's just take a look at a few points on this graph and see if we can figure out what its equation will be. So I'm going to point out that there is a little minimum down there, and that's at negative 4. I know these don't seem like irrelevant points at the moment, but I'm going to point out that these are at negative 2. And I think that's probably all we need for now. So what I want to do now is see if we can build this function up piece by piece. So the base function is going to be y equals x squared. That's definitely a quadratic, mostly because it says so. But visually, it's a quadratic. And then we can ask ourselves, what's happened to that quadratic? And we just have to make sure that we put the letters in the right place, or the numbers in the right place in this case. Okay, so I'm going to do the easy one first. It looks like it's been shifted down 4. And since it's been shifted down 4, I can say that that's x squared minus 4. By the way, I'm not suggesting that these two lines are equal to each other. I'm just developing step by step. The next thing we're going to do is say, does it move side to side? And it does not. So there is no d value, so we don't have to worry about putting anything with the x. And then we have to ask ourselves about a and k. Now, I'll be honest, with a polynomial function, we can always deal with it by just giving it an a value and ignoring the k, because they end up doing the same thing. Whether it's in front of the x squared or in front of the whole function, doesn't make any difference. So here's what we're going to do. Normally, a graph like this, when we go over 1, a quadratic would go up 1. But in this case, it goes over 1, up 2. And because it's going up twice as far as it should, we know that the a value should be a 2. Y equals 2x squared minus 4. Normally, if we went over, let me choose a different color here. If we went over 2, we should go up 4, but I think we're going to go double that. We go up 2, 4, 6, 8. Sorry. How far are we going up here? Oh, why am I counting by 2s? 1, 2, 3, 4, 5, 6, 7, 8. So yep, that's twice as far as we would expect to go up in a quadratic. So I think our formula, our equation that we came up with, is perfectly good. Let's try that one more time with this graph. And again, I'm just going to put a couple of the points on there that may matter. We have a vertex here at 3, 0. And I'm going to put this point and this point on. I'm picking ones that are on grid lines that have nice grid intersections. It doesn't have to be those. I could have chosen that one and that one, I guess. I don't want to pick any one that's going to be not on a grid line because it's just messy to work with. So again, starting off with our base function, that is a quadratic. Y equals x squared. Now in this case, there is no up and down transformation. There's no translation downwards or upwards, so we can skip the c at the end. However, it does go 3 to the right, so that's going to transform into y equals x minus 3 squared, because again our d value is negative, or the opposite sign it should be. Okay, so that takes care of that. Again, for polynomials, we don't have to worry about differentiating a and k. We'll just treat it as the same thing, call it a. We have to figure out what that a value is, however. So normally on a quadratic, if we went over 1, 2, 3, 4, we should go up 16, up 4 squared. However, we're not going up 16, we're going down 1. So that means we're going 1/16 of the amount we should, and in the opposite direction, so negative. So I think it's going to be y equals negative 1/16 x minus 3 squared. And by the way, once you've come up with your theoretical correct answer, by all means, go back, punch it into Desmos and see if it looks correct. But I think that's going to be it. Okay, and I'm just going to test it one more time before I put a nice box around it and say I'm done. Normally, if I went over 8, I went from 2 to 10, so that's over 8. 8 squared should be 64, which means I should go up 64. The negative takes me down 64, and I think it's 1/16 of 64, which should take me down 4. Okay, so that seems to agree with our answer. I say we're correct. And as I say that, I also say we're done with that lesson. Now, I will point out that the homework questions say sketch. I want you to do an extremely rough sketch. That doesn't mean you need a fully numbered axes. They don't need to be like done on grid paper and pretty with a ruler. Just do a rough sketch. I want you to see if you can predict the approximate shape and location of the graph. That's it. Once you've got it in your head, you kind of sketched it out really super quickly, then go into Desmos and verify that it is correct. I don't know why I'm going back to Desmos now. I want to go back to the webcam. There we are. Okay, so that's basically all there is for transformation of functions. Again, I threw in that little bonus of a trig function transformation. We're going to get to that at a different point in the course, but it does really help. It's one of the few types of functions that does really emphasize that there is a difference between the a value and the k value, between the vertical change stuff and the horizontal change stuff. So hopefully that helped justify it, and I will see you in the next lesson. Have a great day. Bye.